In this section, we talk about some mathematical skill. Elasticity rely on the theory of differential equation. So, in order to handle the material deeply, you need to have better knowledge of differential equation. I give you some review about the ordinary differential equation. If you want to have more details, you can consult some books of engineering mathematics. Okay, here I just give you a brief review. In this section 1.4.1, we talk about ordinary differential equation. In example 1, we consider a simple equation like this: y double prime plus 4y equals 0. We want to find out the general solution. The usual way to do this is we let y equal to exponential ax. Okay, and then since we had already assumed this form, we put this form into this equation. And then see y double prime means that you differentiate this function twice to get this one. Okay, and this one, put it here to get this one. Here, this is a square. Okay, maybe the writing is not very clear, but this is a square. Y double prime equal to a square exponential ax. 4y equal to 4 exponential ax. And then we just take this term out because they are common terms. Exponential ax, okay? And then bracket a square plus 4. This totally equals 0. But this exponential function not equal 0. So we know that a square plus 4 equals 0. Okay? And then we move 4 to the right hand side of the equation, and then take the square root. We get a equal to plus minus 2i. Okay, I is the imaginary number. So in this way, we get a equal to plus and minus 2i, and then we put it back to the form y equal to exponential ax. Now a here is plus 2i or minus 2i. And then we use the principle of linear superposition to add these two particular solutions together. The first solution is exponential 2ix, a equal to I, exponential ax, a equal to I. The first solution. The second solution is exponential minus 2ix, a equal to minus 2i, like this. Okay, so we get two solutions, and then we multiply these two solutions by arbitrary constants C1 star and C2 star, and then sum it together. In this way, we get the general solution. Okay, this is a usual way to find out general solution in the theory of differential equation. If you don't understand this technique, you can consult the book again. Now, after we have obtained the general solution, we turn this exponential 2ix into sine and cosine. Exponential minus 2ix into cosine 2x and minus sine 2x. This is called the Euler Formula. And this Euler Formula can also be found in the book of differential equations or engineering mathematics. Okay, we just take it for granted here. So exponential 2ix equal to cosine 2x plus I sine 2x, and this one equal to this. And then we collect the terms to get here. C1 star plus C2 star times cosine 2x plus I times C1 star minus C2 star times sine 2x. And then C1 star plus C2 star to be assumed to equal to a new constant C1, and this equal a new constant C2. And then we can turn our solution into this form. This form, we have y equal to C1 cosine 2x plus C2 sine 2x. See, the key point is we don't have any imaginary number here. I is gone. Okay, in this solution, we have exponential 2ix here. The imaginary number I is not a very natural number, so we don't want to see it in our solution. So we use the Euler formula to modify, to transfer our solution into this form. And in this form, we will be more comfortable because we don't see the imaginary number again. Okay, and this is called the general function, general solution, because we have two arbitrary constants inside this solution. Okay. Now let us look at example 2. It is similar to example 1. See, in example 1 we have y double pi plus 4y equals 0. Now we have y double pi minus 4y equals 0. In the same way, we let y equal to exponential ax, and then we put this into here, and then get this equation. And then y double pi equal to a squared times exponential ax minus 4y equal to this one. And since exponential function not equal 0, so a squared minus 4 equals 0. So a equal to plus minus 2. So a equal to plus minus 2, and then put it back to here. Y equal to exponential plus minus 2 times x. So we have two particular solutions and then put it here. And exponential 2x plus exponential minus 2x with some arbitrary constant as the coefficients. Okay. This is the general solution again. Now, example 3. We have y double pi equals 0, means that this is a more simple equation. Here we have y double pi plus 4y. Here we have y double pi minus 4y. But here we have only y double pi. And then we can integrate this equation to this, because y double pi equals 0 means that y pi equal a constant. And then y pi equal a constant means that y equal to c1x plus c2. It is an easy job. And then we want to say that we can also find out this solution by another way. If we let y equal to exponential ax, we put this into the equation y double pi equal to a squared exponential ax, because we differentiate it twice. So we get this form. Okay, in this way we know that a must equal 0, because this one not equal 0. So a must equal 0. So we have a equals 0, and exponential ax means the exponential 0. So y equals exponential 0. So we have one solution, y equal to c1 exponential 0, means that equals y c1. So we have only one solution, but we supposed to have two solutions, right? See, in example 1, we have two solutions, cosine and sine. In example 2, we have two solutions also. How come we have only one solution, c1 here? So we should add up a supplementary solution like this. This is a common skill in differential equation. Means that when you have only one particular solution for a second order differential equation, you should add another solution like this. You just multiply the first solution by x and then change the coefficient. You get the supplementary solution. In this way, we turn our solution here into this form. In this form, we have two particular solutions. One constant solution, another one is a linear function of x. Okay. Now let us look at example 4. Y double pi minus 4y pi plus 4y equals 0. Again, we let y equal exponential ax. Put it inside this equation. Y double pi equal this one, 4y pi equal this one, 4y equal this one. And then we have common term, exponential ax, exponential ax, exponential ax. So we take it out. And then the whole thing equals 0. So exponential not equals 0. So this one equals 0. So we grouping the term, load that, and we load that this one equal to a minus 2 bracket square. So this not equal 0. This one must equal 0. So we get a equal 2. But now we have double root. We call this double root because we have square here. Means that we can solve this equation twice. Every time we get the same root, a equal 2. So this is called a double root. Since a equal 2, we put it back to y equal to exponential ax to get this one. Y equal to exponential ax means that 2x here. But you have only one particular solution, so we have only one term here, times one arbitrary constant C1. In this way, we should add another solution called the supplementary solution by this. Okay, here we multiply this solution by x to get the second particular solution. The first solution, the second solution, and this one called the supplementary solution. Okay, and this is a common skill, a usual skill in the theory of differential equation. When we have double root case, okay, when you solve the equation, you let some term here, and then you find out that the coefficient satisfy some equation to lead to some double root, and then you should modify your solution by adding some supplementary solution. Okay, let us look at example 5, which are a little bit complicated. First, we deal with the fourth order equation. Okay, here y bracket 4 means that we differentiate y 4 times. And then we have minus 2 lambda square y double pi plus lambda 4 y equals 0. Here lambda is a what? Is a positive parameter. Is a constant, positive constant. Okay. Now we once again we let y equal to exponential ax, and then we put this one into here to get this one. Y differentiate 4 times equal to this term, and this term equal to this term, and this term equal to this term. And then we have the common term. Take out the common term exponential x. We get the coefficient equation. And then we grouping the term to turn this form into this one. Once again, we have the bracket square here. Means that we will have double root. This exponential equation, this exponential function not equal 0, means that this one equals 0. So we have this one equals 0. And then a square equal to lambda square. This is a double root case. And then we take the square root to get a equal to plus minus lambda, in which are double roots. Means that a equal lambda is a double root. A equal to minus lambda is also another double root. Okay, let us deal with the roots a equal to plus and minus lambda first. We get this one. Why? Because exponential ax here, y equal to this one, and a equal to lambda, A equal to minus lambda. Okay? And then we add up together to get the general solution. Okay? But now, this is a fourth order differential equation, and we have only two particular solutions in the general solution. So we need to have some supplementary solution, like this. Okay? C1, C2, and C3. Here, we get, we get this solution from what? From this one. This one, we multiply this one by x to get the third solution. And we multiply this solution by x to get the fourth solution. Okay? So we have only two particular solutions here. But now, 1, 2, 3, 4. We have four particular solutions in our general solution. Okay? This is called the linear superposition. Okay? Another thing we need to say is that sometimes some books, they want to express this function by the exponential function by the what? By the hyperbolic sine and hyperbolic cosine functions, like this. Hyperbolic sine, hyperbolic cosine. And this one, and this one, this one, this one, this one. And then we grouping the term, we get, correcting the term, we get this one, 1, 2, here. And this one, 1, 2, here. Okay? And then the rest will be done in the same way. And then we let this as C1 star, this is C2 star, this is C3 star. Then we get this one. See, this form, this solution is equivalent to this solution. They are the same. Okay? But some author, some textbook prefer to use this form. I don't know why. Maybe they like to have some functions similar to the sine and cosine function. So they use the hyperbolic sine and hyperbolic cosine here. If you write your solution like this, it's completely okay. It is a correct solution. But this solution is a more popular solution. Okay. Let us look at example 6. Now we have one more new things. We introduce the concept of parameter, not parameter, operator, differential operator. See, we have a differential operator here, dx twice. Okay, d square over dx twice minus 1 over x squared, bracket y. This operator can operate to y. This term operated to y, operating to y to get this one, and this term operated to y to get this one. Okay, so this equation is equivalent to this equation. And now we move this term to here. Okay, means that we just multiply x squared in the left and right hand side of the equation. So okay, and then we turn this equation into this one. And we find out that this is called the Euler equation. Okay, let me explain it to you what is a Euler equation. Euler equation is like this. General form of Euler equation. If you have a term differentiate 4 times and the coefficient is a function of x4, then it is a term of the typical term of the Euler equation. See here, y differentiate 3 times and the coefficient is x3. And then if the unknown function y differentiate twice and then the coefficient is x squared. If differentiate y once, and then the coefficient is x1, power 1. So this term, in this form, we have the Euler equation. And the feature, special feature is this. special property is this. If you have an Euler equation, you should let your solution like this, y equal to x a power, okay? Not y equal to exponential ax, okay? See, this one have been used in this equation. This is equation with constant coefficient here. This is constant, this is constant, this is not x. So we let y equal to exponential ax like this. But if your equation is an Euler equation, then you should let your solution like this. Okay? Let us continue our calculation. Since here, this is y differentiate twice, and the coefficient is x squared, and then this is y differentiate 0 time, and the coefficient is x 0 power. So this is a Euler equation. So we let y equal to xa, but not y equal to exponential ax. This is a key point you need to know. Okay. Now once you have this, everything is easy. You just put this one into here. Okay. If you put it here, you need to differentiate twice. This one, y equal to xa, so y pi equal to a times xa minus 1. Y double pi equal to a times a minus 1 x a minus 2. Okay, so we put this one into here and this one into here to get this one. Okay, let us do it here. X squared, this x squared y double pi is this one. Okay, x squared y double pi this one, minus y is this one, and then x squared is here, y double pi is this one, which have been calculated here. Okay, like this, and minus y is this one. Okay, and then x squared times xa minus 2 is xa. So this term is the same as this term. So we take out the common term xa here. Okay, and then this one equal to this one. Okay, and this one equal to this one. So finally, we take out the common term, we get this equation, which is equal to 0. But this one not equal 0, so this one must be equal 0. So we have this, and finally we solve this equation to get this solution. So a equal to 1 plus and minus square root 5 over 2. So we get two solutions. Y equal to C1. See here, I did something wrong. You should change it because we put A into here. Okay, but I make a mistake. I put it into here. Okay, this is the wrong way. I should put this A into here. So please do it like this. Y equal to C1x, and then with this power x, we change little e into little x, and then this the same, and then cancel this one. And then here, plus C2, this little e become little x, and then this one should be erased. Okay. Sorry for making such kind of mistakes. Okay. Let us look at another example of Euler equation. Okay. Here, this is another operator. Here, this one is the differentiation with respect to y twice, and this one is the differentiation with respect to y once. So this one is equivalent to this one. Once again, this is a Euler equation. Why? Because if we move this x into here, we get this one, and then we multiply the equation by x, and then to get this one. Okay, and obviously this equation is a Euler equation. So again, we let y equal to xa, and then differentiate it once, and differentiate it twice. Okay, and then we put this one into here, this one into here. Means that, okay, we write this equation like this. This term equal here, and this term equal here. Okay, because this one is just this one. Okay, with x squared. Okay, and then times x a minus 2. And also this term, it becomes this term. Now we get the common term xa, and then we take it out to get the coefficient equation. But now minus a and plus a will be cancelled out to each other. So we get a squared only. Again, this one not equal 0, but the whole thing equals 0. So a squared equals 0. So we get a equals 0 as a double root, because we have a squared here. So we get a equals 0 as a double root. And then we get one solution only, which is y equal to x0. Y equal to c1 times x0, but it is only equal to 1. Okay? In order to get the general solution, we should add another supplementary solution, log x. See, this is a new thing. Means that in the previous example, we multiply the solution by x in order to get the supplementary solution, like this. Okay, here, yes, this one. Okay, we have double root here. We have double root here. We multiply this solution by x. Okay, to get the supplementary solution. But now the situation is different because we are having the Euler equation. So the supplementary solution should be obtained by multiply the existing solution by log x instead of x only. So here, log x. Okay. Once you understand this, we get another supplementary solution. We got the another solution as the supplementary solution. So we get the general solution of this equation like this. Okay. Now let us look at example 8. Now we have two differential operator here. This is only in this example we have only one differential operator. Now we have two differential operator here. I want to tell you that, see, this differential operator is just the same as this. We only change the independent variable from x to r. Okay, and then we operate it once and then operate it twice. Okay, and then this equals 0. We know that this is a Euler equation. This is a Euler equation. So we let phi equal to Ra, and then we differentiate it once, differentiate it twice, and then calculate this term. Once we do this, we can put it back to this one here, to this part here. We first calculate this part. This one times this one equal to this one. Because here, this means that the differentiation should be the second one. So second order differentiation. And this one, the first order differentiation. So, and then this one is this. This one is this. So we put it here. This one equal here, and this one equal here. And now we take the common term out. Okay. Then after the simplification, this one equal will be cancelled out with this one. We have only a squared here. So finally, we have calculated this term as a squared times r a minus 2. And then we put this one or this one into here, just like this. 0 equal this one, this one, this one, this one. And then this one we place like this. Okay? Now we can perform the differentiation twice to this one to get this one. And then perform the differentiation once to this one to get this term. Okay? So from here we get this one. From here we get this one. Okay, of course we have some common terms. And then we grouping the terms. Actually, we can take a minus 2 out, okay? But I did something stupid. I used a more lengthy way. I just expand this term, a squared minus 5a past 6, and then past this one, and then finally this one and this one cancel out to get this one, this one, this one to this one. Okay, and then this one equal to this one. So finally, this lot equals 0, but the whole thing equals 0. So this equals 0 and this equals 0, like this. Okay, this equals 0 and this equals 0. A equals 0 and A equals 2. But here we have a squared and a minus 2 squared. So we have double root again. The solution is written in this way. Phi equal to C1 R0 and C2 plus C2 R squared, because RA, right? R0 R squared. Okay? And then we know that this is a fourth order differential equation. Now the solution, the general solution is not complete because we have only two particular solutions. So we add up some supplementary solution by multiply this term by a log R. From here, we multiply it by log R. And from R squared, we multiply by log R to get another two supplementary solution. And then we add it up together to get the general solution. Okay? We do such kind of modification because we are having double roots. Okay? Finally, the general solution of this equation is obtained. Okay, in equation line, we solve a little bit more complicated Euler equation like this: 1, 2, 3, 4, 4 terms. And also in here, this one called the Laplacian is formed by two terms. This one means that we differentiate r, little r, twice. This one we differentiate little r once. Means that in this equation, the independent variable is little r. The dependent variable is f. Okay. Since this is an Euler equation, we let the solution like this: f equal to Ra. And then we want to calculate Laplacian f. Laplacian f. Okay, so we put this one into here. And f just like this. And then we perform the differentiation, this one, like this one, like this. And then finally, we get this one, and then this one, and this one. It is an easy job. You can figure out by yourself. Now, once you get Laplacian f, of course you can get Laplacian and Laplacian f. Okay? This one is this one, and this one equal to this one. But Laplacian f now is just like this. So put it here. Okay? And then we perform the differentiation twice to this one here to get this one, and this one to get this one. Okay. Now, after some we grouping terms, we get this one as a minus 2 squared. Actually, such kind of calculation have been done in the previous example, I think you can figure this out by yourself. Okay. Okay. So finally, we can have this expression, Laplacian twice f. Okay. And then we calculate this term here, this term here, this term here. Once we do this, we have this 4 term, 1, 2, 3, 4, 1, 2, 3, 4, and then we can deal with the equation. Let us do it term by term. This one, this one. But now this one is here, and this is Laplacian f equal to Ra. So this is Ra minus 2. And then the Laplacian turn into this form. And then we differentiate this term twice to get this one. And this one to get this one. And after we grouping the term, we get minus 4 A minus 2 square A Ra minus 4. And then the third term here. See, Laplacian f have been calculated. Okay, so we just write it. This one, this one, this one, this one. This one equal to this one. Put it here. Okay, and then this result is easy. And then this term here, f equal to Ra, and then we have this directly. Now we have this one, this one, this one, this one. We put it back to here. Okay, this equation we copy it down here, and then this term, the first term here is this one. We put it here. Okay, let me do it like this. This term, just this term, the result is here. Put it like here. Okay, and then this term is this term. The result is here. We put it like here. And this term is this term. The result is here. We put it like here. And this term is this term. We put it like here. So this one have this one. This one is this one. This one is this one. This one is this one. Okay, they all have the common term Ra minus 2. And then we do some reorganization of the coefficients. Here, A minus 2 square is the common term. We take it out. Okay, this one, take it out. And A square minus 4 here. And then we have the common coefficient minus 4 here. We take it out, it's A square minus 4. But now, once you do this, once you have done this, you understand that this A square minus 4 and this equal to this A square minus 4. So this one is a common term. We can take it out. This one, take it out here. The rest will be in the bracket. So finally, we know that this whole thing equals 0 because this is the equation. This not equals 0, so this equals 0 and this equals 0. When this equals 0 is like this, and this equals 0 is like this. Okay? This equals 0 here. This equals 0 here. A squared minus 4 equals 0, so A equals plus minus 2. And this one means that A minus 2 squared equal to 4. And then so A minus 2 equal to plus minus 2. So A equal to what? Plus minus 2 times plus 2. So A equal to 4 and 0. Okay? So we have 4 roots. A equals 0 and 4, and A equal to plus and minus 2. So finally, we put this A, this 4A, back to here. You know, we have A, back to here. Like this. C1 R squared due to plus 2. C2 R minus squared due to minus 2. C3 R0 due to A0. C4 R4 due to A4. Okay, A equals 4. So finally, we get this solution, and R0 is just only 1. Okay, finally, we use a common skill like this to get the general solution of the Euler equation like this. In example 10, we do a new things again. We have a equation like this, u double pi minus ku. And then we add up some boundary conditions. When x equals 0, u equals 0, and x equals L, u equals 0 too. This one is a common equation. It is a simple equation. This equation is just like the equation before. Y double pi plus 4y, or y double pi minus 4y, or y double pi equals 0. See, if we turn y equal u and 4 equal lambda, and then we get example 10. Right? So the solution procedure is just the same as those in example 1, 2, 3. Okay? Now, we let u equal to exponential ax because this is not a Euler equation. So we let u equal to exponential ax, and then put it to this equation, and then to get a squared minus k. And so we get the solution a equal to plus and minus square root k. Okay? You can figure it out by yourself. It's easy. When k is positive, we have this one. We put it back here, k positive, and then positive square root k and minus square root k here. Okay, this one is just like this one. Yes, here. This one is exponential. Okay. So case 1 is just like example 2. Now, once you get the solution, you put the boundary condition here. U0 equals 0 means that x equals 0 should be put inside. Okay, x equals 0 here. And then x equals 0, this one, x equals 0, this one. And this one equal 1, this equal 1. So we have C1 plus C2 equals 0. Okay, so C2 equal to minus C2, C1. And then another condition, UL equals 0. Okay, UL, put it here. X equal L, put it here. X equal, put it here. And C2 equal to minus C1. So we take C1 out to get this term. But this term not equal 0, so C1 must be equal 0. This not equal 0. Not equal 0. So this one equals 0. And then C1 equals 0. But C2 equal to minus C1, so C2 must be equal 0 too. Since C1 equal C2 equals 0, so C1 equals 0, C2 equals 0. So U must be equal 0. So in this case, we get a useless solution. Okay, trivial solution, doesn't have any applications. In another case, k is negative. Okay, so since k is negative, we must say that this is minus ki, like this, minus ki. Because k is negative now, in the square root, we should modify this term as square root minus k and time I, like this. Okay. If you understand this, we put this into here to get this one and this one. And in the same thing, just like we had done before in example 1, we turn this into the cosine and sine, this cosine and sine. Let me show you. Example 1. Here exponential, we have I here. So we use the Euler formula, cosine sine, okay? And then we finally we get this term. Now we do the same thing again. Okay? This one, cosine sine. And then we grouping the term, we get C1 bar cosine and C2 bar sine. Okay? See example 1. And now we use the boundary condition to get the solution. Let's look at here. X equals 0, U equals 0. But X equals 0, we should put it here. This one equals 0, like this. And this one equals 0, like this. And this one drops out. This one equals 1. So 0 equal to C1. Okay? So C1 bar must equal 0. C1 bar equals 0. So U, this one drops out. In the function U, this one drops out. U equal to C2 star only. Time exponential, this one. So, okay, I do it again. C1 bar equals 0, okay? So this one must be equal 0. So U equal to C2 bar times sine square root minus kx, okay? Just like this. This one equal to this one. Now, once you get this, we put x equals 0 here. Okay, means that x equals 0 here. And then we say that C2 bar not equals 0, because if C2 bar equals 0, then C1 bar equals 0, C2 bar equals 0, then we get the trivial solution again. So we require that C2 bar not equals 0. Once we do this, we get this one equals 0. Okay? If this equals 0, this one equal to n pi, and k equal to minus square n pi over L square. And then we put k back to here, and then get u equal like this. Okay, this is a non-zero solution, and this is a useful solution. See, I will mention that this solution is a basic function for the Fourier series. Okay, we will talk about Fourier series later. See, remember that. Please memorize that this solution is a very important solution, because it gives us the base function for the Fourier series. Okay. In the first case, k equals 0, k positive, negative, and k equals 0. We solve this solution, this equation like this, and then this equals 0 means that u double pi only, and then we get the solution like this. This solution is just like example 3. Example 3 here. Okay, the same thing. Okay. So once again, we put the boundary condition inside this function, and then you can figure out that C2 equals 0, and then Ux equal to C1x, and then you put it here, and then you figure out that C1 also equals 0, so U equals 0. So in case 3, you can figure out by yourself very easily that U equals 0 again. So in case 1, case 2, case 3, 3 cases, only case 2 will give us useful result. Okay? And this useful result related to the Fourier series. And in example 11, we talk about this equation, but this equation is just the same as the equation before. See, u double pi equal to ku. here g double pi equal to lambda g. Okay, you turn k into lambda and then u turn to g, and then you get the same thing. So we use similar technique, g equal to exponential alpha theta to get alpha square equal lambda, and then you get 3 cases: case 1, case 2, case 3. And then this is the exponential part, like this one. The exponential part, and then lambda 0, you get this one, just like this one. Lambda k equals 0, you get this one. And then lambda is negative, you get this one, and then you get this one, which is just equivalent to this. K negative, you get what? You get this one. Okay. So this example is exactly the same as example 10. Why we add this example here? Because later in our applications, when we talk about the theory of the artistic, we need such kind of example. So I put it here. You can figure out this example by yourself. Finally, in example 12, we talk about the orthogonality of Eigen Function. Means that in example 10, we have this equation and the boundary condition. Now the solution is like this. And I want to tell you that this solution is called the Eigen Function, and this one is called the eigenvalues. And one important property is this. The Eigen Function satisfies this integral equality, which is called the orthogonality of the Eigen Function. Okay? Sine n pi over Lx times sine m pi over Lx equals 0 if n not equals m. Okay? This is a very important result later. See, when n equal 2, m equal 3. Here, 2, n equal 2, m equal 3. And 2 not equal 3. And then we don't need to perform the integration because this formula tells us that this equals 0. And n equal 2, we have here. M equal 1 here. If you have this this integral, once again, according to this formula, it is 0. You don't need to carry out the integration in details. Okay, let us give you the proof. In order to integrate this integral, we should use one formula. Sine A times sine B equal to 1/2 cosine A minus B minus 1/2 cosine A plus B. So we can turn this one into this one and this one. Okay, turn the sine into cosine and cosine. Okay, and then once you have done this, this cosine function can be integrated easily to get this one, and this cosine function can be integrated easily to get this one. And then you put the upper bound and lower bound inside this function. Upper bound and lower bound inside this function. Let me do it step by step. Here, upper bound, x equals arrow. X equal arrow. If you put it here, arrow and arrow will be cancel out each other to get this one. And this the lower bound. Lower bound x equals 0. If you put it inside, you get sine 0, right? But sine 0 equals 0. And this one, sine n minus m pi also equals 0. And also we have n minus m here, which require that n not equal m. Okay? In the second part, we put the upper bound x equal L here. And then L and L cancel out to get this one. X equals 0 here. And this one. And sine 0 equals 0, sine this one equals 0. So the whole thing equals 0. Okay? So with such kind of calculation, we understand that these two functions as the Eigen functions, when n not equal m, the integration of them must be equal 0. Okay, this is called the orthogonality of Eigen functions, and this formula is very important because later we will talk about the concept of Fourier series. In that part, we will use this formula again.